talked the other day as well about the unit for charge. What's the unit for charge? Yeah, the coulomb. And we said yesterday or the other day that the coulomb is a really, really big unit of charge. It takes about 10 to the 19 electrons or about 10 to the 19 protons in order to make up a single coulomb of charge. Gives you an idea as to how much a coulomb of charge really is. The charge of an electron, the exact charge of an electron or a proton is found on your data sheet. I'd like you to look on your data sheet right now and tell me in coulombs what the charge of an electron is. Don't do it from memory. Look on your data sheet because it's important that you can find it on your data sheet. The way that it's listed on that data sheet is a little bit different than the way that we really need it here. Yep. Good. So we're going to say the charge of the electron. Q, by the way, is the symbol for charge. So the charge of the electron would be negative 1.60 times 10 to the minus 19 coulombs. The charge of the proton, QP, would be, good, positive 1.60 times 10 to the minus 19 coulombs. And of course, the charge of a neutron would be nothing, right? 0. There's some other things that are listed on the right-hand side of your data sheet with charges as well, like an alpha particle and like certain kinds of quarks. Okay? In the end, the notation is exactly the same. The charge of these things is different than in the electron and proton, but the notation they use is exactly the same. So if you ever see a particle like that, before we really learn about that particle in Unit 5, you still know how to find the charge of it. You might not know what the particle is, but you know how to find the charge of it just by looking at the notation. Now, the next thing we talked about was the difference between a conductor and an insulator. Who can tell me the difference between the conductor and the insulator? Who can give me an example, a good example of a good conductor? Everybody should be able to give me an example. Maria? Metals in general, right? Specifically, maybe something like silver, which is a really good conductor, or gold, which is a great conductor. Copper, aluminum are great conductors. What makes aluminum a better conductor than, let's say, glass? What makes aluminum a better conductor than glass? Yep. Yes, yes, absolutely. It allows the flow of electrons. And why does it allow the flow of electrons better than glass? What's special about aluminum, copper, gold, silver, and so on that's not special about glass and wood and plastic and rubber and so on? What's special about the atom itself that allows the flow of electrons? The electrons in these metals in the outermost levels aren't as tightly bound to the nucleus, right? So it's a little bit easier to cause those electrons to leave. If you want electrons to flow, you got to get electrons leaving that atom, right? It's a lot easier to get electrons to leave the atom of aluminum than it is to leave the atoms that are in this compound of rubber or whatever the case may be. We have varying degrees of conductivity. Everything will conduct to some degree. So when we say an insulator, okay, it doesn't mean that it won't conduct electricity. It just means that it won't conduct electricity nearly as well as something like aluminum or steel or something like that. We also talked about 3 laws. Well, we really talked about 4 laws, but there's 3 of them that kind of go together. And then there's the 4th law that's kind of separate from the first 3. The 3 laws of electricity, this is back in grade 5. Hey, my son last year, when he was in grade 5, looked at electricity, and he learned the 3 laws of electricity. Probably not quite to the detail that we will learn them over the next several days, but he learned them. You can list the 3 laws of electricity, right? What's the first one? I don't even care what order you give them to me in. Tom? Opposite charges attract. Good. So positive attracts negative, negative attracts positive. Good. Okay, easy enough, right? What's the next one? Simon? Good. Like charges repel. So positive repels positive, or negative repels negative. What does the word repel mean? Sometimes we get hung up on something like that, right? We can remember the definition, but then when we go back to think about what it really means, we have trouble with one of the words in the definition. What does the word repel mean? Attract means pull together. Repel means push away, right? So positive pushes away positive, negative pushes away negative. Finally, what's the third law? Be careful with your wording here, okay? Because a lot of people will get the gist of it, but miss a very important word here. Tom, what is it? Good. You're going to learn today why charged objects attract neutral objects, but why a proton doesn't attract a neutron or an electron doesn't attract a neutron. That neutral thing has to be a neutral object that consists of protons and neutrons, not just protons and electrons, not just neutrons. Okay? The final thing that we learned here on Tuesday, I guess it was, the final thing that we learned on Tuesday was this law of conservation of charge, which says almost the same thing as the law of conservation of anything else. Okay, the law of conservation of blank says blank can't be created or destroyed. So the law of conservation of charge would say that charge can't be created or destroyed. It can be transferred. Okay, when you walk across the carpet with your sock feet on, okay, you transfer charge either from you to the carpet or from the carpet to you. You become charged, the carpet becomes charged. That's why when you touch somebody, you give them a shock, right? Or you touch the light switch, you give it a shock. Or you receive a shock, however you want to look at it. Charge can be transferred, but it can't be created or destroyed. So the total amount of charge that we have when we start has got to be the total amount of charge that we have when we finish. The number of protons is the number of protons. The number of electrons is the number of electrons. We just shuffle them around a little bit. Hey, if we're going to shuffle something around, though, what's it going to be? The protons, the electrons. The electrons, how come? Yeah, they're orbiting around the nucleus, and they're held in place around the nucleus. And there's the protons and neutrons in the nucleus. The electrons, as they orbit around the nucleus, they're held in place. They're attracted toward the nucleus by an electric force that you're going to learn more about tomorrow. But that electric force is relatively strong. It holds them in place pretty good. But it doesn't hold them in place as well as the force that acts between the protons. There's an attractive force between the protons called the strong nuclear force, which at small distances, and of course in the nucleus we're dealing with really small distances, it's a really, really strong force. Okay, so those protons are held together really, really, really tightly. Okay, it is possible to break up that nucleus, but it's not normal to break up that nucleus. It's a lot easier. Okay, you rub two things together, you put a little bit of kinetic energy in there. It's not enough energy to blow up the nucleus, but it is enough energy to blow up the rest of the atom, essentially, is to take some of the electrons and move them off somewhere else. All right. Let's give you a little example of a type of a problem that we did on Tuesday, okay? Let's say we have three objects, all of which have a charge of something. The first one, we're going to say Q1. We're using that symbol Q now for charge, right? Q1 is going to be minus 10 microcoulombs. Q2 is going to be positive 5.0 microcoulombs. And Q3 is going to be positive 3.0 microcoulombs. Here's what's happening, okay? 1's going to touch 2, then 2's going to touch 3, then 1 is going to touch 3. So we got three stages here. 1 touches 2, then they're separated. Then 2 touches 3, then they're separated. Then 1 touches 3, then they're separated. I want to know what the charge on all three of these objects becomes after I do all of that touching of 1 and 2 and 2 and 3 and 1 and 3 and so on. So let's draw a little chart here. Okay, we got three charges, 1, 2, and 3. They start off as minus 10, plus 5, and plus 3 microcoulombs, right? Just do it in microcoulombs. The standard unit for charge is a coulomb, but if you're doing a problem like this where you're just averaging things together, there's no reason why you have to do the conversion there, right? Just leave it as microcoulombs. Okay, so we're touching 1 and 2 together here. 1 touches 2. Minus 10 and plus 5. When we touch them together, assuming they're more or less equal size and more or less equal shape, then they're going to balance out. In other words, they're going to average. What's the average of minus 10 and plus 5? Minus 10 plus 5 divided by 2. What's it equal? Minus 2.5. So they balance out to be minus 2.5. The third one remains plus 3. Then 2 touches 3. 2 touches 3 now. Minus 2.5 plus 3. Add those up, it gives me 0.5. Divided by 2, it gives me 0.25. So they're going to balance out to be 0.25. Whereas first one, it's now minus 2.5, isn't changing in this little generation of touching. Stays minus 2.5. Finally, charge 1 and charge 3 touch each other. Minus 2.5 and plus 0.25. Let's add them up. Gives me minus 2.25. Let's divide by 2. Add them up, divide by 2. Minus 2.25 divided by 2 would be minus 1.125. And the second charge stays where it was at 0.25. So we started off with these big charges, minus 10 plus 5 plus 3. And now we're dealing with really, really small charges. Does that seem right? Well, let's do a little check here, okay? The law of conservation of charge says the total charge throughout this whole thing has to stay the same. They can move around, but the total charge has to stay the same. So add them up. Minus 10 plus 5 plus 3 gives me minus 2. Minus 2.5 plus 3 gives me minus 2. So far, so good. Minus 2.5. 0.25 gives me minus 2. So far, so good. And finally, minus 1.125, 0.25 minus 1.25 gives me minus 2. So the total charge throughout here has remained the same, even though the charges I'm dealing with now individually are much smaller than the charges I was dealing with when I started. Good? I wouldn't want to say that this will appear on your diploma exam, but there's a pretty good chance. Usually you see one of these questions that appears, certainly on your unit test, okay? If not on your diploma exam coming up at the end of January. Honestly, it's not usually, usually it's 3 objects, maybe a couple of steps as opposed to 3 or 4 steps. Okay, but in the end, if you can do 3 steps, you can do 2 steps. Sometimes it's part of a bigger question as well. Okay, but if you do this, you're well on your way to solving that question. All right, today we're going to talk about how we can charge objects. Okay, we've talked about the fact that you can charge objects. Right? You walk across the carpet with your sock feet, you touch somebody, okay, you discharge or you transfer electrons to that person. We can charge objects. You can charge your feet by walking across the carpet. You can charge the other person by touching them with your finger. What are the mechanisms by which we can charge objects, by which we can transfer charge? Well, there are 2. One's called charging by conduction, and one's called charging by induction. Conduction always involves, every single time, always involves a transfer of charge. So you will always move charge from one object to another if you're charging by conduction. Induction never involves a transfer of charge, not directly at least, a transfer of charge. Conduction usually, although not always, usually involves contact, usually involves the 2 objects touching each other. You walk across the carpet, you charge yourself by walking across that carpet, you're touching the carpet, right? There's contact with the carpet. You touch the other person to shock them, there's contact with the other person usually. Okay? There's touching involved. When you're charging by conduction, it usually involves touching, although there are exceptions to that, and we'll talk about that in a few minutes here. And induction never involves touching. So if you're asked a question, you're given an example of charging, of something becoming charged that wasn't charged before, and there was a transfer of charge, you know right away it's got to be conduction. If there isn't a transfer of charge, you know right away that it's got to be induction. If the objects touch each other, you know right away it's got to be conduction. If the objects don't touch each other, all bets are off, right? Okay, it's probably induction, okay, but there's no guarantees because conduction can also involve charging by not physically touching, just that it usually involves touching. Okay, we're going to break these down now into a couple subcategories. Charging by conduction can be broken out into charging by friction and then charging by contact, which sometimes charging by contact, we don't even give it a separate name. We just call it charging by conduction. They're both conduction, but sometimes contact, we just call it conduction instead of contact. Charging by friction involves rubbing things together. And when you do that, electrons will move from one to the other. This is governed by the law of conservation of charge. Okay, if I have two objects that are both neutral and I rub them together and one becomes +5, the other has to become, what's the answer to that question? Okay, if they're both neutral, rub them together, one becomes +5 coulombs, the other has to become -5 because they have to, they're not balanced out here, right? Okay, this isn't like the problems that we were doing just a minute ago in our review here. Okay. But it's still governed by the law of conservation of charge in that the total charge still has to remain the same. By the way, the one that became +5, did that gain or lose electrons? Did it accept electrons or did it give away electrons to the other object? We know it's electrons that are transferred, right? I want to know which one receives the electrons, which one gives away the electrons. +5, does it gain or lose? Sorry? Lose. Yeah, it's going to lose because it's positive, right? You don't get positive by adding negative to it. You get negative by adding negative to it. So the one that's +5 gave away its electrons to the one that becomes -5. Charging by friction. There is, by the way, in your textbook and in a whole lot of other resources, books, internet, whatever, something called the electrostatic series. Okay, you don't need to be familiar with that electrostatic series, but what it does is essentially ranks all these different materials, okay, from silk to glass to a million different materials. And it basically says, okay, the higher up on the list it is, the more likely it is to lose electrons. So if you rub something high on the list with something low on the list, the one that's high on the list loses electrons, the one that's low on the list will gain electrons. That's what helps us to determine, let's say when I rub a balloon against my hair, which way the electrons go. Do they go to the balloon or do they go to the hair? Well, we check that electrostatic series and that would tell us which way they go. Okay, don't panic about that, but that is in your book if you're curious. Charging by contact or charging by, sometimes we just call it charging by conduction, simply involves two dissimilar charges. In other words, two charges that are not the same. One might be +5, the other might be +4. One might be 0, the other one might be -50. Two charges that are not the same. They don't have to be opposite. Okay, they can both be positive, both be negative. They just can't be the same. They either touch each other or they come really, really close to each other so that charges will jump. Ironically, charging by contact doesn't actually have to involve contact. You walk across the carpet. You ever notice this sometimes? You walk across the carpet, you touch somebody in the finger, and the charge actually, actually get the shock before you actually touch the person. We'd still call that charging by contact. It's still transferring charge, and it's not rubbing together. It's the same thing as if you actually touch fingers or whatever. So we're going to say charging by contact or charging by conduction involves touching, although I'm going to put that in quotation marks because, remember, it doesn't actually physically have to involve touching. Touching two objects with different charges together. What do you think happens when you touch those two things together? It's governed by the law of conservation of charge. If you touch -5 with -7, they're going to balance out to be -6 and -6. That is assuming the objects are roughly equal size and equal shape and same material. That's the one we were talking about in our example of conservation of charge today, and the one that we gave in our example of conservation of charge on Tuesday. Now, if you don't like seeing a chart like this with a whole bunch of words, the good news is there's going to be some pictures for this one. Now it gets exciting. Charging by induction, which never involves a transfer of charge, never involves touching, does involve two subcategories. One's called a temporary separation of charge. The other's called a permanent. So you can induce a temporary separation of charge, and you can induce a permanent charge. What do each of those mean? Well, let's draw a picture for the temporary separation of charge. Here's a neutral object. I've got it drawn with two positives and two negatives. Two protons, two neutrons. But understand, I don't really mean two protons and two neutrons. I mean 38,147,000 whatever protons and the same number of electrons. Right? Equal numbers of protons and electrons. So it's neutral. I bring a positively charged object nearby. Again, I've got positives drawn there, no negatives. I don't mean there's just protons. I just mean there's more protons than electrons. It's positive. What's going to happen now as a result of bringing that positive nearby that neutral object? Two questions. First of all, what's going to happen to the protons in that neutral object? What's going to happen to those pluses in the neutral object? Anyone? Yep. They're going to get pushed away, right? Good guess. That's what everybody always says, but not quite right. They do want to get pushed away because they're repelled by it, right? Like charges repel each other. But the protons, they're pretty tightly bound in that nucleus. So where are they going to go? Pretty much nowhere. And they're going to pretty much stay where they are. They want to be pushed away, but they really can't be pushed away. Not that much. They stay where they are. What's going to happen to the negatives, the electrons? Simon? Yep. Well, that's a good question. If it's something like we're talking about a solid material here, but if we're talking about a gas or a liquid, then absolutely the entire nucleus could move. Yes, yes, it could. So let's assume a solid, though. I should have prefaced that by saying that it was a solid, and the atoms themselves aren't going to move around, which of course could happen in a gas or liquid. What's going to happen to the electrons, though, even if we have just a solid here? They are going to move, right? They are going to move, assuming that the positive charge on this guy right here is strong enough. These guys are going to move. Where are they going to move? Which side? They're going to be pushed away to the left or pulled towards the right? They're going to be pulled towards the right. Notice what we've got here now. One side of this neutral object, it's still neutral, right? But one side of the neutral object is positive. One side of the neutral object is negative. Now, I'm oversimplifying this a little bit. Not all of the negatives are going to be pulled to that side. Right? Some of the negatives are still going to be on the left-hand side. The net effect is that the left-hand side will be positive and the right-hand side will be negative. We call that a separation of charge. It's still neutral. The object isn't positive or negative. It's still neutral. It's just a separation of charge. Why do you think we add that word temporary on there? Why do we call it a temporary separation of charge as opposed to just a separation of charge? What do you think happens when I take that thing away? It goes back. There's no reason for the separation to remain because the thing that was doing the charging, the thing that wasn't touching, and the thing that wasn't transferring is no longer there. There's no reason for them to stay there. So they're going to go back to where they were before. It's a temporary, because it's not permanent, separation because it doesn't actually charge the object, positive or negative. It just pushes or pulls the negatives one way or the other to make it positive on one side and negative on the other side. Let's draw another picture here. So there's my neutral object. This time I'm going to bring a negatively charged object nearby. Again, not just electrons. There's billions of electrons and billions of protons there. We're just more electrons than protons. Okay, what's going to happen, Bo? What's going to happen to the protons in this one? They're not going to go anywhere. Good. They're going to stay where they are, assuming it's a solid, right? What's going to happen to the electrons in this one? Oh, go ahead. Yeah, they're going to be pushed away. Good. So it's going to look something like this. Again, not all of them. We're drawing it as if all of them are going over there. That wouldn't happen, right? But the net effect is that the left side is negative and the right side is positive. I want you to notice one thing here. The side of the object, the neutral object, closest to the charging object is what? In both cases, relative to the charging object. See, the side of this neutral object up here is negative. The charging object was positive. The side of the neutral object here is positive. The neutral object, sorry, the charging object is negative. So the side that's closest to the charging object is always going to be opposite. Now listen very carefully. Yesterday or 2 days ago we introduced this, and then earlier today we reviewed this. The third law, Tom said today, of electric charge is charged objects attract neutral objects. Protons don't attract neutrons. There's no fundamental reason why a positive, electrically, why a positive would attract a neutral. But there is a reason why a positive would attract negative and why a negative would attract positive. The reason that charged objects attract neutral objects is because they induce a temporary separation of charge. And when you do that, the side that's closest to the charging object is always opposite. So now it comes down to that first law. Why do charged objects attract neutral objects? Because positive attracts negative, and negative attracts positive. Does that make sense? So now we know why it's not enough to say charge attracts neutral, but charged objects attract neutral objects. You got to have that movement of electrons within that neutral object in order to get the temporary separation of charge, and you got to have that temporary separation of charge to get that attraction going on there. Right, Kenton? So how do we make it permanent? How do we make it permanent? Well, we're going to introduce, last thing for now, and then we'll take a little bit of a break here. We introduce what we call a ground wire. A ground wire could be literally a wire that goes into the ground, or it could be some other kind of conductor that will allow electrons to drain from something or to pull electrons up from the ground or something bigger. The symbol for a ground wire is this. The third prong of the plug in your, when you plug everything into your house, the third prong is a ground wire. It goes directly to the ground, literally directly into the ground. If you look outside your house at your power box, at the power meter, that is, you may see this copper wire that's about the thickness of your pinky finger that literally runs down beside the plastic pipe that goes into the ground. It will end 4 or 5 feet into the ground and go nowhere. It's a ground wire. Okay, it literally goes right into the ground. You may not see that because sometimes those ground wires are covered with some kind of plastic pipe. Okay, they're not always, but sometimes they're covered with this plastic pipe. Bottom line is your house has one. It has to have one. They never used to, but they all have to have them now in the last, I don't know, 40 years probably. Because what it does is allows electrons that are doing things they're not supposed to be doing, like when wires arc or something like that, it allows electrons to go down into the ground instead of just causing your wires to heat up and cause a fire. Okay, so it prevents fires. And that's what the third prong of the plug goes directly into the ground. So let's introduce this ground wire, this wire that goes directly to the ground. What's going to happen now in this first case? Nothing's going to happen to the protons, right? Well, yes and no. Yes, and yes, it does actually. It does. You're right. It does, but it does it only in the case of when it's needed. So in the sense that you've got something happening that's not supposed to be happening. No, not at all. But you've got that arcing or whatever taking place, then these electrons will be drained, which is better than the alternative, right? So what's going to happen here? Nothing's going to happen to the protons. What's going to happen to the electrons? Well, these electrons that are right here that were pulled to the right are going to stay there. But now, look, you got the Earth that's attached to it. The Earth is massive. It's what we call an infinite source and sink of electrons. We can take as many electrons as we want from the Earth, and the Earth pretty much remains neutral. Or we can add as many to the Earth as we want, and it pretty much remains neutral. So now what we get is a bunch more electrons coming up from the Earth. Well, we now no longer have a positive side and a negative side. Look at what we got. We got a couple positives and about 20 negatives. Now what do you have here? It's not a separation of charge anymore. It's a negative object, right? It's a negatively charged object. But what happens when you take that away? Why would they stay? It's like this is the guy that everybody likes. Okay? This is the party here. This is the guy that everybody likes. Everybody comes up from the Earth to go to the party because this is the guy that everybody likes. As soon as he disappears, what happens? It's like, well, why would we stay? Why would we stay up here? The guy that we came up to see is gone. Why would we stay? We go right back down into the Earth where we came from. Unless, before this guy disappears, you cut that. You cut the path. You don't give him a path to go back. Then you take this guy away. And what happens? They might say, oh, geez, I want to go back. I don't want to be here anymore because the guy we came to see is gone. but they can't get back because the tunnel has been filled in or whatever. Does that make sense, guys? What about right here? Okay, what about in the bottom one here? We've got this negative object that's nearby this neutral object, charging by induction, temporary separation of charge. Okay, but now we've got it grounded. What happens to the protons? Nothing happens to the protons. What happens to the electrons? This isn't the guy that everybody comes to the party to see. This is the guy has a little bit of body odor, has a little bit of social ineptness. Nobody really wants to see this guy, so what do? They run away. They go as far away as they can. They go down into the earth. So these negatives that were over here on the left-hand side are now going down in there. Now we've got just positives in there. Now it's not just a separation of charge. Now it's positively charged. But this guy goes away. Everyone says, hey, it smells okay in here now. Okay, the guy that nobody really wants to see is gone. So what happens to those guys that went down into the earth? Let's come back. Let's come back up now. Unless everybody says, yeah, you know what, we're happy with who's here. Let's cut the ground wire. Then they can't come back. Now we're left with a permanent positive charge. Good. Now, some people would argue that, hey, look, we transferred electrons here. We transferred electrons down this way in the bottom one. That's conduction, isn't it? Well, yeah, it is kind of. There's conduction taking place within there, but the overall process we still call induction because the thing that's doing the charging, this guy right here, the cool guy that everybody likes or the smelly guy that nobody likes, they're not touching and they're not transferring charge. So the overall process would still be called induction. Okay?